Hello, my name is Rachel, and this is my video entry for Case Study 2. I have picked Case 2 and Case 3 in this video. I will start by explaining Case 2. The MRI above shows a large tumor with areas of necrosis within the tumor. Here. And on the right is a PET scan from the same individual following administration of fluorescently labeled D-glucose. First off, I will start by explaining how these tissues uptake glucose. In the liver, the glucose uptake in the fed state glucose uptake into the muscle and adipose tissue is controlled by insulin, which is secreted by the beta islet cells of the pancreas in response to an increased concentration of glucose in the portal blood. In the fasting state, the glucose transporter of muscle and adipose tissue, GLUT4, in intracellular vessels. These insulin-sensitive tissues only take up glucose from the bloodstream in the presence of the hormone. As insulin secretion falls in the fasting state, the transporters are internalized again, thus reducing glucose uptake. In the skeletal muscle, the increase in cytoplasmic calcium ion concentration in response to nerve stimulation stimulates the migration of the vesicles to the cell surface and exposure of active glucose transporters whether there is significant insulin stimulation or not. It is through GLUT4 transporters, which are insulin dependent and thus need insulin present to bind these transporters, which then allows them to transport glucose. This happens in the fed state, where it is high in glucose that is stored as glycogen, and in the fasted state, the glucagon that is released will have no effect on skeletal muscles because they do not have glucagon receptors. However, like in the liver, they will take up free fatty acids to form ATP to continue with cell processes. In the brain, glucose is taken up in GLUT1 and GLUT3 transporters. This occurs at an insulin-independent manner, thus allows the brain to continuously intake glucose to perform its functions. The glucose uptake is only used for glycolysis in the brain. It is not used for glycogen synthesis. However, in the fasting state, the brain still regulates glucose. If it does not get it from glycogen stores, it gets it from the liver, when it releases glucose into the bloodstream during the release of glucagon. In the adipose tissue, it uptakes glucose through GLUT4 transporters. As mentioned earlier, GLUT4 transporters are insulin dependent. Therefore, this uptake only occurs during the fed state when glucose levels are high and insulin levels are high. Next, I will talk about Case 3. Case 3 looks at a 5-year-old patient who is brought into the pediatrician's office. The mother had noticed some symptoms in the child. The symptoms she noticed were persistent thirst and frequent urination. Right off the bat, these symptoms had shown that this patient had diabetes. And to test for diabetes, blood samples are taken for insulin measurements both at time 0 and 1 hour after a glucose loading test. The results for the little boy is shown in this table here. The baseline for the patient's insulin level was around 0.8, which is quite low as a controlled patient should be around 6. After 1 hour, the insulin levels were still very low at around 5, when a controlled patient was around 40. These tests again suggest that the patient has diabetes, specifically type 1 diabetes, as he is not able to produce insulin. Insulin is a very important hormone in regulating glucose uptake. Without it, GLUT4 transporters cannot transport glucose into certain tissues, specifically skeletal muscle and adipose tissues. Because these tissues do not receive glucose, the patient would often be very weak and tired. The prediction of the patient's fasted glucose levels due to diabetes will be very high blood glucose levels. Due to the hypoglycemia present at the beginning of the fasted state, which causes the liver to release an excess amount of glucose, causing it to be very high. 2 regulatory enzymes that are likely to be active in this individual's current condition is most likely from the liver. As it is insulin independent and are continuously active. The first one is glucokinase, which will phosphorylate this glucose to make glucose 6-phosphate, which is then used for different things in the cell. The next one is glucagon synthase, which converts glucose 1-phosphate into glycogen through the process called glycogen synthesis. So in the fat state, glycogen synthase is dephosphorylated and it is caused to be active. These 2 enzymes, as they are present in the liver, which is able to transport glucose in, even with insulin deficiency, will cause them both to be active in this patient. That will conclude my video entry for this case study, and thank you for listening.